Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We're in this AP Physics C Mechanics curriculum. Also your engineering physics mechanic, one of the first physics classes in your engineering program. Unit 2, still on Newton laws of motion. We have a few more videos in this unit, but we're getting there. Today, the last two videos, we talked about free body diagrams and using those with Newton's second law with like a box on a table. Then we did a video on ramps, and then we did a video on interacting blocks. We're going to combine all of that today with the ramps and the interacting blocks with this pulley system. So we're just going to get started. This is a massless pulley, so we know from the past videos, and if you don't know that and you're just jumping on, you want to look back on the video right before this on our playlist for this unit, because I'm going to explain to you, I explained to you that the massless pulley means that T1 is going to equal T2, and that T means tension. A lot of times you'll also see it, as force of tension 1 equals force of tension 2. It means, but you can, however your professor or your teacher does it is the right way. They mean the same thing and interchangeable. So I'll try to keep it consistent with this force due to tension. Anyway, so because we have the massless pulley, we know that's what that means. That's our big red flag that, hey, we can assume that. We have coefficient of friction is 0.20. That means that's your red flag. Hey, this isn't a smooth surface. If they say it's a smooth ramp, that means you don't have friction. You don't have to worry about it in your free body diagram. But we do have coefficient of friction, which means there is friction on this ramp. It's a rough surface. Mass 1 here is 1 kilogram. Mass 2 is 2 kilograms. Our theta, our angle of our ramp, is 30 degrees. They want an expression for acceleration, and they want it with the givens in that expression, the variables of our givens, and constants, which means little g. We're going to get started. In the last video, I'm not going to explain a lot of this because the last video I really went into the explanation on these interacting blocks with pulleys. But we're going to sum this as a system, sum our forces, and we're going to sum our forces parallel to acceleration. And when you have interacting blocks, every block means you need a free body diagram for that block. So I'm going to do block 1, and that's here. It's on the ramp, so I have my little dot that my block becomes a dot. We can do that in physics. I'm going parallel to the ramp, and that's that normal force. Sometimes you'll see it as force normal like that, but your normal force. You have a force due to gravity of block 1, and we talked about that in the last video. You need your subscripts because we have two different masses we're dealing with here, and you do not want to get them confused, and you hate to go through all of this trouble on these problems and really understand what you're doing, but you get your masses mixed up. All right, so that's M1G. Okay, now I have tension going up the ramp, so that's going to be my force of tension 1. And then because it is moving up, I'm going to tell you that block's moving up and this block is moving down. Friction always opposes motion. So if this block is moving up, that means friction is down the ramp. Now, if this were reversed, and this block were bigger and it were moving down the ramp and this one was raising up, then friction would be up the ramp because it would oppose motion. So just make sure you understand that. And that's kinetic friction, it is moving. That's block 1. Block 2 done. Block 1 is done. Block 2, it's a little bit less complicated. We have tension. That is that force due to tension 2. I tried to make this arrow and this arrow the same length because they said it's massless, so we know they're equal, so I tried to make them the same magnitude because magnitude is depicted by the length of that arrow. Then I have force due to gravity down, and it's got to be longer. It's got to be unbalanced because this block is moving down. So that's force due to gravity of block 2, which is M2G. All right, I'm ready to go. I'm ready to sum my forces parallel to the ramp. And remember, when we do this as a system, it's going to be your total mass. I am defining this direction as positive, up the ramp for block 1 and down for block 2, because that's the direction of acceleration. And that's going to be my positive direction. So here we go. I'm going to start with block 1. I'm looking for all forces parallel to that ramp, parallel to the string, parallel to the acceleration. That's my positive. All right, so I have force to tension, that's up, that's the direction it's moving, so that's positive force tension 1. I have friction that's down the ramp, so that's going to be negative. And then you might want to stop there and start moving on to this block, but you cannot. Because in that last video when we were doing ramps 2 videos ago in our playlist, remember that this is force due to gravity. That is the hypotenuse. You can't do this on your free body diagram, but we have force due to gravity perpendicular to the ramp, because here's the ramp. And then we have a force due to gravity parallel to the ramp. And this is theta, if this is theta. All right, so I have force due to gravity parallel to the ramp, and it's down the ramp, which is negative. So that's going to be a negative force due to gravity parallel from block 1 on that ramp. Then I'm going to go to, I'm not done yet, no equal sign, I'm not done yet. I've got to go to block 2. Okay, block 2 has a tension and a force due to gravity of 2, or weight, we call that weight. Both of these are parallel to the string or parallel to the direction of acceleration. So force tension though is opposite of the movement of that block. So it's going to be negative. So we have a negative force of tension 2, and then we have a positive force due to gravity, and the whole thing is parallel. It's not, oof, that was awful. I don't know what I was doing there. So let's fix that. Yee. All right, it is parallel. Like in the instance of block 1, it's force due to gravity. There was a component that was perpendicular and a component that was parallel. For block 2, all of its force due to gravity is parallel, so it's in the direction of motion, which we defined as positive, so there we go. And that equals total mass. You can't just put mass now, total mass. So that's m1 plus m2 times our acceleration. Now, I know that my tensions, you may need to make this statement. By the way, the AP board loves this problem. Whether it's multiple choice or a free response question, they love this problem. So, you need to make this statement that these two are equal, and then you can cross those out because I have a positive tension and a negative, so they cancel out. I have a negative kinetic friction minus, now my force due to gravity, parallel. We know this, parallel is sine, so that's going to be force due to gravity of block 1 sine theta, which means m1g sine theta. If you didn't follow that, and that equals that force due to gravity parallel. If you didn't follow that, go back to my ramp video. I explain that in much more detail so you can understand that. All right, but we're going to m1g sine theta. Because again, that's opposite that angle, and this is the hypotenuse. All right, now we've covered those two, and they're both negative because they're both down the ramp, okay? Now we get to our positive force due to gravity 2, which is just m2g equals m1 plus m2 times our acceleration. All right, we're almost there. We could divide both sides by m1 plus m2 to get an expression for acceleration, which is what we're looking for. However, we have one variable that was not given. Mass was given, g, little g is a constant, theta was given, so we're good except for friction. It's always that friction force that throws us, and we've got to do more steps. So I'm going to go over here. We know that friction, and this is going to be friction on block 1 only because that's the one that's on the surface. We're ignoring air resistance here, so there's no friction with the air for drag. It's only friction with the surface, so we're only talking about block 1, is mu, the kinetic friction, times the normal force. All right, because physics is fun. All right, so here we go. We know that friction is mu, but now we've got to figure out what the normal force is. And you're like, oh, that's easy, it's mg. No. It's not mg. It's not weight or force due to gravity, because force due to gravity was straight down. Only a component of that was perpendicular and opposing normal. So you cannot say that normal is mg here. Normal is equal, if we summed these forces, and I'm going to go ahead and do it in another color so we don't get lost here. If we sum this force perpendicular to that ramp for block 1, that's going to equal just the mass of 1, because we're only doing one block now. It's not a system. We're not adding it, to the perpendicular acceleration. Well, this block is not moving vertically at all. It is only moving parallel. It's not, I said vertical, I'm sorry, perpendicular to the ramp. This block is not jumping up and down off the ramp. It's only moving parallel. So acceleration perpendicular to that ramp is 0. All right, well, I have normal up minus my force due to gravity perpendicular for block 1 equals 0. So normal equals the force due to gravity perpendicular. So this has to balance my force due to gravity perpendicular, or you could say the perpendicular component of weight, or the perpendicular component of force due to gravity. Those are equal. Well, that is adjacent to that theta. So that is actually, I'm going to put it right here, mg, and that's going to be m1 because we're talking about block 1, mg cosine theta. Again, if you don't follow why that is, one, I told you in the video with ramps, you need to memorize this, and you need to memorize this. That force due to gravity perpendicular is mg cosine theta, and parallel is mg sine theta. And I explain why that is, but that is cosine to that angle, and force due to gravity, or mg, is the hypotenuse. Okay, perfect. I'm going to put that in for my n. So now I have m1g cosine theta times mu is now my kinetic friction. All right, so I'm back. I'm going to put that in here. I have a negative mu m1g cosine theta. Okay, and that's all negative, minus an m1g sine theta plus m2g. And I'm going to divide that whole thing by this m1 plus m2. This little expression here I'm going to divide over. So equals your acceleration. And it's ugly. It's so ugly. But you now have an expression for acceleration. I didn't tell you this would be pretty. But this is one of the reasons the AP board loves this problem. All right, so remember we have coefficient of, so all we did was sum our forces parallel to our strength. Sometimes when you get to this point, you're like, I don't even know what I did. Is this right? I don't even know. What happened? What happened? So let's go over it. We summed our forces parallel to the string, or parallel to the motion, parallel to acceleration. We had a tension and a friction and a parallel component only of that weight for box 1. 1 was up the ramp, 2 were down. Then we went to block 2 and we had a tension force and a weight force that were parallel to our acceleration, but one was opposite the motion, so opposite what we called positive, so it was negative, and then that weight from block 2, which was m2g, was positive. All right, then all we needed to do was find an expression for friction on that block 1. We know friction equals coefficient of friction times normal, that fun formula, but we had to go find normal, and normal was not mg because this isn't setting on a flat horizontal surface, it's on a ramp, so normal is actually equal to only the perpendicular component of weight, which is mg cosine theta. So we came up with friction. Perfect. If you were to go put in your numbers, 0.2, 1, 9.81, theta was 30 degrees. Then same thing here, then M2 was 2 kilograms and 9.81. And then this would be 3 because it's 1 plus 2, you get 3. You would get an acceleration here of 4.34 meters per second squared. Now, here's what happens. On occasion, you might get your negatives mixed up. Okay, and if you get down here to acceleration and you get a number that is greater than 9.81 meters per second squared, let's say you get 15 meters per second squared, abort, abort, abort. That is a no, because free fall is 9.81. It's not falling faster than free fall. Okay, you've got tension here. So that's always a good indicator logically. Is this less than 9.81? It's a good indicator, we like that. Now, the next thing they might ask you to do, and then we're done with this video, is they might say, hey, find an expression for tension, and what is the tension force in this string? Oh, okay. You're like, but wait a minute, I canceled out my tensions in the system, so what do I do now? Okay, what you do now is you go to an individual block to find an individual force. So we're going to go to block 2. Why block 2? Well, because just by looking at it, this looks like a mess. And this looks a lot easier to handle. That's why we go to block 2. Time is never your friend in a physics exam, ever. All of my physics exams in my engineering program never was physics. Never was time, my friend, ever. So go with the easiest, quickest one. All right, I've got block 2 that's got 2 forces, one that's opposing the motion, one's with the motion, and there's a tension, so I'm just gonna do that. I'm gonna say, hey, I've got my negative force of my tension 2 plus my force due to gravity, or my weight, whatever you wanna call it, of that block 2, equals the mass of block 2, because I'm on an individual block, so individual mass. When I'm doing a system, total mass, okay, times my acceleration that I know. I'm going to add my force of tension over and subtract this expression. So I have force due to gravity 2 minus mass 2 times my acceleration equals my tension force from block 2. We know this is just m2g. So I'm putting in m2g minus m2a. So mass times little g minus mass times that acceleration I just found equals my tension force. And if you put in 2 times 9.81 minus 2 times 4.34, you get a tension of 10.9. Now, here's the deal. We said that these are equal. So you could do it for this block 2, block 1. You have force of tension, up would be positive, minus friction, minus my force due to gravity parallel, because remember in this one we would have 3 forces, 1, 2, and 3 parallel forces, 1 positive, 2 negative, equal the mass of block 1, which was just 1 kilogram, times the acceleration, which was 4.34. You get the same answer. You get 10.9. All right, so all good. And I think that's it. Hopefully that helps. We are now moving on to a sign that will be hanging from 2 strings, and we'll be looking at that problem. And then we're going to be moving on to interacting blocks where they're sitting on top of each other or side by side. Those are our remaining videos in this unit. So just a few more to go. And thank you for watching. If you like these videos and you're watching them, we would love for you to subscribe. If you have friends that are taking this class with you and they need help and they're helping you, we would love for you to share it. And thank you for all your comments out there. They've all been positive. We love them. We try to respond to everybody in a reasonable time frame. And thank you for watching, and happy physicsing.